got involved in setting up the networks at the time. The early 1990s, the Ethernet was just becoming deployed, and Sun Microsystems workstations were everywhere, especially in physics. And I got interested in setting up this network and understanding how it worked. And for me, as a physicist, it was interesting to learn everything about how these computers worked, and over time get my hands dirty, making all the changes, installing them, changing them, and understanding them. But over time, I decided I wanted to understand them as a natural phenomenon, much as you would understand physics. Instead of figuring out how to program them. And
I'm sorry, we had some problem with the audio. I'll start the streaming again. All again. Sorry.
Good morning, everyone, from around the world. It's my honor to be able to open all the talks for Patrick this morning, and wishing you all the best in these strange times. My name's Mark Burgess, and I'm probably best known for writing the open source tool way back in the beginning of open source known as CFEngine. And out of that story came something called promise theory, which eventually also became associated with CFEngine. I want to talk a little bit about the origins of that to you today, because it's a story that's a little bit misunderstood. Let me tell you a bit about myself, for those of you who don't know me. I was trained as a physicist. I went to university to do a doctorate in theoretical physics. And when I finished, I moved to Norway as a postdoc, and I got interested in computers. I was never that interested in computers when I was younger, unlike perhaps some of you. My first computer program was a drum machine, and then I got interested in 6502 assembler, adventure games. I was never a gamer, but I liked adventure games because I was interested in the understanding of language and machine intelligence and stories like that. Now, when I went to Norway to become a postdoc in physics, I got involved in setting up the networks at the time. The early 1990s, the Ethernet was just becoming deployed, and Sun Microsystems workstations were everywhere, especially in physics. And I got interested in setting up this network and understanding how it worked. And for me, as a physicist, it was interesting to learn everything about how these computers worked, and over time get my hands dirty, making all the changes, installing them, changing them, and understanding them. But over time, I decided I wanted to understand them as a natural phenomenon, much as you would understand physics. Instead of figuring out how to program them and assuming they would do what we want them to, because we all know that computers only do what we want them to some of the time. Rather, I wanted to kind of observe them like animals in the wild, see how they behaved, understand if there were any natural phenomena associated with networks of computers, and get to grips with that problem. So I started to automate the configuration and maintenance of these systems. That sounds like a strange idea, to maintain computer systems. It wasn't an idea that people had at the time. It was pretty much assumed that you would install a computer and then it was done, it was finished. Everything would work, you would do your programming, your writing, whatever it was, and on you would go. But as a physicist, I knew that systems degrade over time, and they become engaged in all kinds of interactions and come under load, under pressure, and they behave differently when they communicate with one another. So I really got interested in this idea of collecting data to study the systems. The origins of CFEngine came out of that. 1993, I started programming the first version. I decided to give it away as an open source GNU project. It was adopted by CERN. I gave some talks there. And the GNU project really helped me to disseminate this around the world, and many people started to use this. I went to America in 1997 to share this at the Usenix LISA conference, and that was the first time I really tried to explain my thinking to manage the systems by making changes and corrections, for example, garbage collection. or configuration of software. Now, back in the beginning of Unix, there were many different kinds of workstations. There was the AIX, Apollo, HPUX, Ultrix, many others. These Unix versions were quite unlike the Linux that dominates the scene today. They were all very different from one another. Even the Bourne shell was very different on each system. Sometimes it was BNSH, sometimes it was the Z shell. I think that was AIX. And so you couldn't write one script that would work everywhere. The layouts of the systems were different. Everything was very, very different. So I realized you would need a layer of abstraction on top of that to make those differences go away. And this immediately introduced the notion of virtualization, which is, of course, now a very well understood thing. But we needed to virtualize the concept of a machine, create a model around it, and then this notion of desired end state came about, where we have some idea of how we want the systems to behave, how we want them to be configured. Instead of making a lot of changes manually, we would simply try to define the desired end state and make the machine home in on that state, a bit like driving with a GPS. So the desired end state becomes your final destination, and the machine figures out how to get there. This was in contrast to the preferred idea, which was called congruence, where you start the system in a known state, a blank state, a fresh installation, and then you make a number of changes one after the other to try to bring it to the desired state. The problem with that was that it's fragile to the smallest intervention and the smallest miscalculation, and environmental influences often make it go wrong. So you don't necessarily end up where you thought you would. When I went to America to explain this, nobody really understood what I was talking about. And I got a bit depressed, and on my way home, I got sick on the plane. And I started to think about the idea of immune systems making us well after sickness. And could I use that as an idea to explain this notion of desired end state computing? So I went back the year afterwards and gave a talk which was called Computer Immunology, 1998. And this talk described a lot of the ideas of scale, maintaining, repairing a system over time from a single machine to networks of machines. Eventually imagined a day where there would be so many machines that we could just scratch a few skin cells away as we do in our bodies, and it wouldn't matter. The system would be resilient to that change. So we could lose a few systems and it would still carry on working. Back then, 1998, this was a pipe dream. Today, of course, with the cloud, this is the normal practice. Today we have this idea, just show me the code, just make it happen. And we kind of reject the idea that we need to understand something deeply. If we can make things happen, if we can pull the strings to make a computer dance, fine, then we control it. Of course, this is quite wrong. But I wanted to get to the bottom of this problem, and I started to study everything that I could. As time went by, I decided we needed data. So to understand computers, we needed to measure them. I built into CFEngine this capability of unsupervised machine learning, a very simple way of collecting data and building it up over time. And even though the original analyses were manual, you could eventually automate some of that as well, and turned it into a self-regulating, almost alive machine living system. This was my dream at the time, to create a completely autonomous system of local agents that could learn and adapt over time, but still maintain this desired end state policy. Most of the metrics that we're able to measure about systems have almost nothing to do with the behavior of the system over time, certainly not in a way that can be used to adapt or make changes. And even today, we measure almost nothing useful about the systems that we use. But around 2000, I was in America and was actually given an award, the Sage Lifetime Achievement Award, for contributions to the area of systems. And I felt a bit guilty because I didn't feel as though I understood these systems very well at all. And I wanted to go back and understand more. For me, a watershed moment happened when I started to work with some colleagues from Telenor here in Norway. Another physics friend of mine, Jeffrey Canright, and his colleague Knut Enger Monsen got interested in graph theory, and we actually worked for a little bit on search algorithms like Google's PageRank using notions like network centrality. From this, I got a love of graph theory and understood how networks could be described and how different parts of a network play a different role in understanding the outcomes of a cooperation. A key point here is how influence gets transmitted through networks. And I wanted to build this into management systems, but didn't fully understand the mechanics of it. So I went to the drawing board and I tried to really get to grips with the theory of cooperation. And it's a surprisingly difficult thing to do because we imagine this is something that's been studied at length, but in fact it hasn't. There are theories like game theory, there's queuing theory, there's the Axelrod's theory of the evolution of cooperation. All of these things I spent a long time studying, including the bioinformatics of DNA analysis, thinking that perhaps somehow this might relate to the error correction aspects of machines and so on. Eventually, I came up with a simple understanding of what was missing, and that was this notion of intent. You know, as a physicist, we're very obsessed with measurable, numerical, quantitative results, but quantitative is almost useless to describe intentional systems. We need to understand the semantics. So promise theory started as a graph theoretic language for measuring the intentional states of systems and describing their relationships to one another. Eventually, this led to books which are now my treatise on systems. You can take a look at some of those. But in 2004, I eventually realized that I came up with a summary which we now think of as promise theory as a kind of graph of intentions. Computers are not just dynamical systems as I'm used to describing in physics. They are intentional systems. They have a purpose. Purpose is not something we understand in physics, but it is something which is absolutely essential to understand in computer science. So to bake intent into a network, I needed another idea, and this concept of promises turned out to be an answer. Around this time, I got to know another colleague, Jan Bergstra, who eventually wrote the promise theory book with me 10 years later. And he got interested in this. His background was in the logic of processes. And at first, he was very skeptical of this notion of networks and promises and non-determinism, because the whole of computer science is built on the idea of deterministic change. But as he got more interested in this idea, he became converted towards the idea of promise theory and became a contributor. And he pushed me to think about things like trust and the role of what I now call imposition in networks. Over many years, we started to develop this theory. And I realized I could rewrite CFEngine entirely based on this promise theory, given this new understanding of how networks came together. The interesting part of promise theory for me is that it exposed a simple algebra of cooperation, that we can describe the basic ingredients of cooperation in a network, independent of programming languages, independent of tools. It's simply about one party having something that can be offered, something they can intend to do, and other parties being willing to make use of that intention to do something, and the communication between them. Building up networks in this way revealed that both, it wasn't like the regular theory of networks where you push packets and packets are received automatically. It's more like you offer something and the other party has to accept it, as we see more in cases of access control in security, for example. This meant that networks are actually more complicated than we'd given them credit for in queuing theory and network analysis. You had to understand the intentions, the policies of both parties to understand how interactions would take place. So all of these ideas started to come together. At the time, I was an associate professor at the University of Oslo, and associate professors are hired, but I was nominated to become a full professor. And for those of you who don't know, a full professor, a fully anointed professor, is this strange animal which has to be appointed by an international committee. On my committee was Stephanie Forrest from Santa Fe Institute, University of New Mexico, who was also interested in this idea of computer immunology, but for security purposes. And I met some of her colleagues over time, and this helped to develop the notion of immunology and interactions for security policy. We can think of the maintenance of a system as the correction of errors relative to its policy, a little bit like the copying of DNA. So we began to develop this idea, and over time began to see how these networks of connections between not only machines but different states could form a proper semi-mathematical theory of intent. It became clear from studying the machine learning traces that we couldn't understand computers simply on the basis of what we wanted. We also could see the influence of humans on the system in the traces, in the graphs, and the resource dependencies. And this meant that computers won't necessarily do what we want them to do as the programmers. They will do something which is related to what everyone in the world is trying to get them to do. And in the age of the internet, influences come from all around the world at all times, especially on very busy servers performing services online. So what do I want to say about promise theory? For me, this has been sometimes difficult personal journey. The computer science community certainly tried to reject it in the beginning, and still do today. I still get hate mail from some parts of the world. What I want to get out of this is a sense of bringing computer science or computer technology into the realm of science in a way that it hasn't been in the past. Making things work is not science, it's technology. To do science, we need to have an understanding, a theory, and we need to connect it to a bigger picture. One of the interesting aspects to come out of promise theory is its connection to knowledge representations, and now what we would think of as artificial intelligence. From the simple machine learning that I implemented back in the mid-90s to deep learning tools that are available today, machine learning has come a long way, but artificial intelligence and knowledge representation goes far beyond things like that. It goes to graphs of representations between concepts, which connect processing to the theory of computation and beyond. And this is an aspect of promise theory which I think can still be developed more in the future, and is going to be really important to understand how to build our future systems. There are many lessons that come out of this and many general principles that come out of the basic elements of the algebra of cooperation. Another one that was very interesting for me was later I got to know my friend and collaborator Daniel Mezek, who came out of the Agile community. And he got interested in applying promise theory to the notion of how humans work together and especially manage and lead teams in organizations to undergo change. The notion of change in human systems is quite interesting. Of course, humans are very different kinds of agents to the kinds of machine agents that typically run computer networks, but still the principles of cooperation are the same. How one agent will make an offer or a promise to another agent has to accept that, and in order to make use of it. That coordination and cooperation doesn't take care of itself. It requires careful alignment of the kind that we tend to take for granted in IT, and we absolutely shouldn't. Gradually over time, as IT systems came to study more complex networks of interaction, especially in the case of services and so-called microservices, the algebra of cooperation between them has played an important role in how we understand the scaling of systems. And those basic principles of self-healing, desired end states, automatic error correction that were built into CFEngine became adopted in tools like Kubernetes and the auto-scaling, elastic scaling functions that we see in cloud today and take for granted today. So I feel very much that those early studies, although rejected by computer science, are very much vindicated in the field of practical computing. So with that, I'm going to leave the origins of promise theory for for now, and I hope you all have a fantastic day giving your own talks, and perhaps some of you will revisit some of my books, and I certainly hope to hear back from you in the future. So have a great day and stay safe.
Okay. Hello, Mark.
Hi there.
How are you?
I'm doing fine.
Okay.
Working.
Okay, we have some questions here. So the first one is, how do you see the relationship of DevSecOps and Promise Theory?
This is a great question. Patrick and I had a bit of a discussion about this online a couple of weeks back. I think there's a lot of ways in which promise theory can contribute to DevSecOps. Even in DevOps, of course, DevOps became famous for being about cooperation between the dev teams and the operations team, rather than simply throwing things over the wall, imposing upon one another, expecting without really communicating. So the idea that we can understand that more deeply with the theory of cooperation is obviously an advantage. One of the things we talked about in that session was also where security fits in, because whereas perhaps developers and operations folks have clear things to work on and can make changes for themselves, security people often have to seek the cooperation of others to get their stuff done. They're not directly with a hand on a lever or pushing a button or something like that. So it's, I think there's a lot of places where cooperation as an idea plays a big role in DevOps and DevSecOps.
Okay. Any advice to new people in the field?
New people in the field should definitely read as much as they can. Look back at old ideas, because not everything is brand new. Don't believe that just show me the code is not the right answer. Do study up and try to dig deep into ideas, because that's where the real knowledge is.
Oh, great. And do you have something that you would do different in your career?
That I would do differently?
Yeah.
Oh, I would be much more successful. I would make lots more money.
Yeah, that's.
I think that's what I did wrong.
You have a Udemy course, right? So you have an Udemy course. So
yes, that's right.
The course. So where can people sign up?
Actually, if you go to my my company website, ChiTek-i.org, see if I can write that somewhere. Where do I write that so that everyone can see it? Is that in the live comments or?
What?
Where can I write the link to that course
so
that people can see? Should it be in Slack maybe?
You can change me, send me in the chat, so I'll put as a banner.
Okay, let me see, private chat. This is the link to my company website, and there you'll find a lot of information about where to find courses and the conversation that I had with Patrick Dubois about DevSecOps and the online courses and the books, all the books.
Okay. So that's it. Mark will be available at our Slack at the channel Track DevSecOps. So you all can ask him directly there. We'll go forward with Michelle's talk. Thank you, Mark, and it's always a pleasure to see your talk.
Thank you so much, and thanks for hopefully liking my hastily thrown together talk. It was great fun. Thank you. Bye, everyone.